Hello, welcome back to this channel. In this tutorial, we are going to talk about matrices. Now, what is a matrix? A matrix is a rectangular array of elements. So the element in the array can be numbers, parameters, or variables. And a matrix is denoted in the form m by n, where m represents the rows and then the n represents the columns. Okay, so a matrix is given in this way, where we have the first element represented as A11, the second element represented as A12, the third element represented as A13, up to the last element of the first row. And then when we come to the second row too, we have A21 representing the the first element in the second row, and then we have A22 representing second element in the second row, and the second representing a number or an element in the second row in the second column too as well, up to the last element. Now here too, meaning to the last element of that particular row and that particular column too as well. So if you are given a matrix like A equals 2, 1, 4, 5, 6, 8. Now this matrix is a 2 by 3 matrix. Why? Because the number of rows that we have here, we have 1, 2. So we have the rows to be 2 and then the columns as well to be 3. So we have 1, 2, 3. Great. Now, if we have this, let me rewrite this particular matrix again. 2, 1, 4, 5, 6, 8. Now, 2 is in the position of A11. Why are we saying that? 2 is in the first row and in the first column. So first row, first column. Then 1, 2 is in the first row but second column. So we have A12. So it is in the first row but in the second column. Now let's take a different element like 6. 6 is in the second row, right? And in the second column too as well. So A22. That is for 6. Let's take 8. 8 is A23. That is in the second row and the third column. Great. So here the matrix is denoted. We are referring to the matrix A here. The matrix denoted by A equals to AIG by M by N, or simply A equals to AIG. So the I represents the row and then the J represents the column too as well, or the column position of that particular element. So where I equals to 1, which is to the last element, which is M, and J equals to 1, which is said to be in order M by N. Great. Now let's look at this example. So with this example, we have A to be equal to 5, negative A3, 2, negative 1. So let's now take the positions of these numbers. So we have A11, A12, A12, then we have A13. Great. So we have A13 here. So this one we have A21, A22, A23. Great. Now we are saying that we should specify the dimension of A. So what is the dimension of A? We have 2 rows, that is one here, another one here. So 2 rows. Then how many columns do we have? We have 1, 2, 3. So we have 3. Therefore, the dimensions of A is 2 by 3. This matrix is a 2 by 3 matrix. Now the second question says we should find A21. So what is the element in the position of A21? So A21 is what? 2. Now what about A23? Can you get me the answer? So A23, let's look at the matrix again. A23 is what? 7. Great. Now we said we should use the subscript notation to denote the entry of 3. So where is 3? 3 is here. So the subscript notation of 3 is A13. Now let's check the answers in the next slide here. Okay, so we have this one. Now let's check this too. So the solution, as I said earlier on, this is a 2 by 3, and then we have A2, 1, 2, 3, and then 1, 3 as well. Great. Now let's look at addition, subtraction, and multiplication of matrices. Okay, now suppose we have a matrix which is G equals this and then P equals that, and we have to find G plus H. Sorry, this is supposed to be H. We are supposed to find G plus H. So as usual, when matrices have the same dimension is when you can add or subtract. So a case like this, here we have 2 by 3 and another 2 by 3. So this matrix is possible to be added. But a case where we have one to be 2 by 3 and the other one is of different dimension, then it becomes impossible to be added. Okay, that is fine. So now that we have spotted that both of the matrices have the same dimension, then we are good to go. So here G plus H, we are going to have 5, negative 8, 3, 2, negative 1, 7, plus 2, negative 1, 3, 1, negative 3, 5. So here we add corresponding elements. So 5 plus 2, we are going to get 7. The negative 8 plus negative 1, negative 9, 3 plus 3, 6, 2 plus 1, 3, negative 1 plus negative 3, negative 4, 7 plus 5, which is 12. So this is the answer for the addition of the two matrices over here. Great. Now let's talk about the second aspect of the question, which is the subtraction. Okay, so we have this same matrix, that is 5, negative 8, 3, 2, negative 1, 7, minus 2, negative 1, 3, and then we have 1, negative 3, 5, and we have to subtract. So as usual, we subtract corresponding elements. So 2 from 5, which gives us what? 3. Then negative 1 from negative 8. So negative 8 minus negative, so here we are going to get negative 7. Great. This one too, we have to subtract 3 from another 3, which is 0. Then 1 from 2. So 1 from 2 is what? 1. And then 1 from, this is negative, negative. So we are going to get negative 2. Subtract 5 from 7, 2. Which we are going to get 2. So this is the answer for the two operations. Now let's check their solutions. As I said earlier on, this is the solution for the first one. As usual, that is exactly what we have here. And this too, the same thing that we have for the second one. So adding corresponding elements, as I said, we have 5, 2 from 5, which is the one we were here, and that is 3. And then negative 1 from 8, which is negative times negative is as positive. So we are going to get negative 7. And then this 1, 2, 3 from 3, which is 0. And then 1 from 2, which is what? 1. the negative, negative giving us positive. So negative 1 plus 3 giving us 2. Then here to 7 minus 5, which is 5 from 7, which gives us 2. Great. Now let's talk about scalar multiplication of matrices. So let's say we have a matrix V equals to this. So V equals 7, negative 9, 6, 6, negative 4, 12. Suppose we want to find 5 of V. This is the scalar that we are talking of here. So here the scalar is 5. So 5 times V. In this case, we are going to multiply all the elements of the matrix V by 5. So 5 times 7, 5 times negative 9, 5 times 6, 5 times 6 here again, 5 times negative 4, and 5 times 12. So 5 times 7, 5 times negative 9, 5 times 6, and that is what is here. 5 times this 6, 5 times negative 4, and 5 times 12. So 5, 7, 35, 5 times negative 9, negative 45, 5 times 6, which is 30, 5 times 6 again, which is 30, and then 5 times negative 4, which is negative 20, 5 times 12, which is 60. Now let's talk about multiplication of matrices. So here we are going to talk about multiplication of matrices. This is a very crucial aspect that we need to be very careful of. Now, before you can multiply two or more matrices, then you need to check their dimensions. So what do I mean by here? Now, if you have a matrix which is 2 by 3, so here we have 2 rows, then we have 3 columns. Great. And this one too, we have 2 rows as usual, and then here we have 3 columns. Now you see that, how do I check that these matrices are possible or impossible to be multiplied? So here I have the first one 2 by 3, and the second one too is 2 by 3. Now we need to check this side. You see that here and here are not the same, are not equal. In this way, we can't multiply them. So the multiplication becomes impossible when we spot that this side, the column of the first or the column of the first matrix does not or is not the same as the number of rows of the second matrix. Then it means that the matrices are impossible to be multiplied. So now let's go to the, so we have to check whether these are possible to be multiplied or not. Now let's check this one. We have A to be 3 by 2 matrix, B to be 1 by 4 matrix, C to be 4 by 3 matrix, and then D to be 2 by 1 matrix, and E to be 2 by 4 matrix. Now let's check whether these ones are possible to be multiplied or not. So as I said earlier on, B is 1 by 4. So 1 by 4 multiplied by, and C is 4 by 3. So 4 by 3. Now let's check the number of rows. The number of columns of the first one is 4. Now let's check the number of rows of the second matrix is 4. Since these two are the same, it means that we are going to have 1 by 3 matrix, which is possible to be multiplied. So when we check that, the number of columns is equal to the number of rows of the second matrix or the subsequent matrix, then it is possible to be multiplied. Now let's check the second one. B is 1 by 4, and then D is 2 by 1. Great. Now let's check the dimensions and see. So the number of columns of the first one is 4. The number of rows of the second one is 2. They are not the same. It means that this one is impossible to be what, to be multiplied. So that is one of the ways to check if the two or more matrices you are supposed to multiply is possible or not. Let's check another one too here. So we have A 3 by 2. Then we have D2. D is what, 2 by 1. Then we have C. C is 4 by 3. Good. So now we can take two at a time. So let's take A and D at a time. So we have here and here to be the same. It means that we are going to have 3 by 1. Great. Let's dot it with 4 by 3 and C. So here we have the C is 4 by 3. Great. So we have 3 by 1, then 4 by 3. So here we are going to have, because this one and this one are not the same, it means that this one is also impossible to be what, to be multiplied. That is great. Now let's check the last one here. We have DB. So D is 2 by 1. 2 by 1. Then we have B to be what? To be 1 by 4. Then plus 2E. Where is E? E is 2 by what? 4. So now let's take it at a time. So 2 by 4. We are going to have this one. So this is, we have the same number here. We have 2 by 4 plus another 2 times 2 by 4. And this is possible. That is great. So this is possible to be added, because you are going to have a 2 by 4 dimension, which is what, possible to be added. Great. Now let's look at a question on multiplication of matrices. Now, before we multiply, we can check whether it is possible or not. So here we have 2 rows and then 3 columns. Here too we have 3 columns, 2 rows. So 2 by 3 dots, 3 by 2. So this one are the same. So it means that the final result is going to be a 2 by 2 matrix. 2 rows, 2 columns. Now let's check and see. It means that this one is possible to be multiplied, and that is great. So now let's check. We take this one, use it to multiply this. You get it? So here we are going to have 2. Sorry, this one, as I said earlier on, if we are checking if this one is possible to be, I think I made a mistake here. This is cancelled. It's impossible to be added. Great. This one is impossible to be added. So this one is what we are going to multiply here. So multiplying, I think I made a mistake here. It's supposed to be negative 6, 5, 13, 12, 10, 2. So 2 times negative 6, negative 1 times 5, 3 times 13. So that is what you have here. 2 times negative 6 plus negative 1 times 5 plus 3 times 13. Then afterwards, we take this one and use it to multiply the second column too. So 2 times 12 plus negative 1 times 10 plus 3 times 2. And that is what you have here. Then you come down to take 1 and negative 3 and 5. So 1 times negative 6 plus negative 3 times 5 plus 5 times 13. Then you take this same thing again for the second column. 1 times 12 plus negative 3 times 10 plus 5 times 2. And that is it here. So 2 times negative 6 plus negative 1 times 5 plus 3 times 13 gives us 22. So when you evaluate this one, you're going to get 40. And when you evaluate this one, you are going to get 44. And when you evaluate this one, you are going to get negative 8. So before you even multiply, you can use the dimensions to determine whether it is possible or impossible to be multiplied or not. Now let's look at some special matrices. Now, these are some of the special matrices. So we have the first one, square matrix. So a square matrix is a 3 by 3 matrix. It means that a square matrix is of the order m by m, where the number of rows is equal to the number of columns. So when it happens like that, we call that matrix as a square matrix. A square matrix. Great. Now we have some other types of square matrices. So when we have a matrix like this one, we have, let's say, 1, 2, 5. Then we have 2, 8, 9, and then 5, 9, 4. Let's say this is a square matrix where the number of rows equals to the number of columns. We are saying that if Aij equals to Aj, it means that when we arrange this one in a different way, like we are going to make all this column become rows. So we are going to have 1, 2, 5. Arrange this column 2 in a row. 2, 8, 9. Arrange the last one. 5, 9, 4. You could see clearly that this matrix is equal to this matrix. Therefore, Aij equals to Aji. That this matrix is equal to this matrix. Then when it happens like that, we call such a matrix symmetric. Symmetric in a sense that when you arrange the row or when you turn the rows to become columns, it will be the same as the first matrix or the original matrix that you had. That is what you call a symmetric matrix. A symmetric matrix. After making a rearrangement, you see that they are the same. When it happens like that, we call it a symmetric matrix. Great. Now we have another one called a skew symmetric. A skew symmetric. So if you have a matrix, let's say a matrix of the form this, and you take negative of it after making a rearrangement and you take negative of that, for example, what happened here, then you say the matrix is a skew matrix. We call it a skew matrix. Great. So in a skew matrix, it means that we are going to when you rearrange the elements by turning the column elements to become row elements. When you do that, we say you are transposing a matrix. So in that case, we can say that a skew matrix is like A negative A transpose. So when you transpose a matrix, you write a superscript T on top to show that you have transposed the matrix by making a rearrangement by turning all the column elements to become row elements or vice versa. When you do that, you say you are transposing the matrix, and when you negate a transpose matrix, then it becomes, and it is a square matrix, then it becomes a skew symmetric matrix. That is great. Now we have another special matrix called diagonal matrix. A diagonal matrix is a matrix with all the elements 0. except the leading diagonal. So when you say the leading diagonal, then you are talking about these elements. They are called the leading diagonals. The leading diagonal. So when you have a matrix with all the elements 0 except the leading diagonals, then we call such a matrix a diagonal matrix. Then let's talk about a unit matrix. If you have a matrix where the leading diagonals are all units or 1, it is called a unit matrix. Then a null matrix is where all the elements in the matrix is what? 0. So that one I won't talk much about it. Now let's talk about a transpose of a matrix, as I've already said something earlier on about it. Now we have a matrix A to be 1, 2, 5. When you rearrange by turning all either the column elements to become row elements or the row elements to become column elements, then you see that you have transposed the matrix. So already we had 1, 6, 1, 2, 8, 7, 5, 9, 4. So we are going to make a rearrangement of A, which is transpose of A. And this is the original matrix. So we are going to arrange all or turn all the column elements to become rows. So 1, 6, 1. This one 2, 2, 8, 7. And this one is 5, 9, 4. When you do that, you say that you have transposed the matrix. Great. Now when you do that, you see that the element here, this is m by n, they will interchange their positions already. So it will become n by m. And that is what we are trying to see here. Now let's talk about another special matrix called an upper and lower triangular matrix. So when you have um, a matrix of the form this, that is a square matrix. This is a square matrix because it's a 3 by 3. All the rows and columns are the same. So this is a 3 by 3 matrix. So this is a square matrix, of course. Now, if you have a square matrix that has the 0 elements below, so here we have the 0 elements below, then this is called upper triangular matrix. Now, when you have the zeros above the diagonals, then this is called a lower triangular matrix. If you have the zeros, or if you have the zeros below the diagonal, then it is called upper triangular. Then when you have above the leading diagonal, then you see that this is what a lower triangular matrix. Now we have another type of, or a special type of matrix called singular matrix. I don't want to waste time on it. A singular matrix is a matrix that has its determinant to be 0. And then we have a non-singular matrix whose determinant is not 0. Now let's look at another special matrix called the submatrix of a matrix. Now, if you have a matrix, say A, which is equal to this, we can have few submatrices of A. So we can take this one, it's a matrix. We can take 1, 0, which is also a matrix. Then we can take 1, 5, it's a matrix. We can take 1, 0, 5, 2. So 1, 0, 5, 2 is also a matrix. So, but the matrices 1, 4, 1, 0 are not submatrices of A, or in other way 1, 4 and then 0, 2 are not submatrices of what? Are not submatrices of A. That is that. So If you have any question, you can send your question to us in the comment section. Thank you very much, and don't forget to subscribe to our channel.